So in the last class, we have stopped and we'll continue in this lecture about message formatting. So now we are sending the messages in different forms. One you can see through mail we send, one with the WhatsApp. Like this, we have so many other online applications where we send messages. So how this messages has to be sent? What should be the format? So that's what here we'll be seeing in this lecture. So message format. The format of the message depends on the objective of the message facility and whether the facility runs on a single computer or on a distributed system. So that's what here, this is a general format where you can use this format for a single computer or for a distributed systems also. So the figure down, it explains a general message format, showing the typical message format for operating system that supports variable length message. So what do we mean by variable length message means? So maybe one person will be sending only one word. Other person may be sending message in one paragraph. So based on that, so here the length is different. For one person may send only one word, other person may send it for 10 words. So that's what here variable length message means. Length may be varied. Okay. So general format of message. So what are required for any message to be sent? When we are sending, we just know only sending. So in the same way in mailbox, if I want to send a message, a mail to your thing, then what I require your mail ID. Because without your mail ID, I cannot send you because I should know where I have to send. So like this, along with that, I should have my mail ID to send to your thing. So then what are the things we require along with that? In our mail there are so many other options. Same way you see your WhatsApp. So what we require for WhatsApp, my number is required and your number is required to send a message for one. So in the same way now it is improved. This is only for one to one or it can be for a group. So now I want to send a group, then how can I send? I'll send like that. Okay, so now we see general format of the header, message format. In that we have two things. One is header and another one is a body. In the header, what are the required things? Message type. So what type of message you are sending? Whether you're sending text, whether you're sending video, whether you're sending message, image, whatever the message type. So whether integer, whether character, like that, the message will be given which type. Destination ID, to whom I have to send this message. That's what. If it is WhatsApp, I should know your number. So if it is mail ID, I have to know your mail ID. Same way here, destination ID is required. In the same way, source ID, I have to send. So if I want to send a message to you through WhatsApp, I should have my number. That's what source ID. Message length, it depends whatever length you can give. Either it can start from one word, you can go to a complete length. The length may be varied. Then control information depends upon what type of control we have to do. So suppose let me come back for mail. Uh, for mail, we don't have any option saying that whether they have read your message, your mail or not. We don't know. So there is no acknowledgement in the mail. Whereas in our WhatsApp, the line changes to a color, then we know that okay, he has read. Means what? Acknowledgement is also I'm getting. So for that we have something called as a control information. And in body we have a message content. So that's what here the explanation of what I have just explained. I'll just go through it. The message is divided into two parts. One is header and another one is a body. The header which contains information about the message. Yes. The header may contain an identification of source and intended destination of the message. That's what require identification of source and identification of a destination. And along with that, we should have a length. Message. What is the length of the message? And type of the message, what various types of messages we are sending. Additionally, we have one more thing called as a control information. Example, pointer field. So a linked list of a message can be created. A sequence number to keep track number and order of message passed between source and destination, and priority field. So that's what I told in this control information. We have so many things. That's what so many things is. Suppose if my message is only one word, then only one block is required. If my message is 10 words or more than one paragraph, then I cannot send at one time. Then what we do, we pass small, maybe five words at one time, 5 words at one time. So that's what here it can be broken. And in the same way, suppose if there is some message which is very important, then I should set a priority field. That's what a priority field is also required. All these are present in a control information. What is the message content we have? Whatever you type, that will be present in a body which contains the actual content of the message. So what you want to type, that will be present in the body. So that's about a message format. Next, we move on to a queuing discipline. So what is queuing discipline is, what should be the discipline for any queuing. The simplest queuing discipline is a first come first out mechanism. If I say very simple one, that's what we have seen even in a scheduling algorithm. So what should be there for a CPU to get complete its work? We have so many scheduling algorithms. Same way here also, we have a simplest queuing. If we see it is very simple, then what it is, first in first out will be the queuing discipline. But this may not be sufficient if some message are more urgent than others. Suppose this is okay if it is first come first serve, but sometimes there may be very urgent message to be passed. In that case, we even require a priorities. An alternative is to allow the specifying of the message priority on the basis of message type or by destination by the sender. Another alternative is to allow the receiver to inspect the message queue and select which message to receive next. This is what is called as a queuing discipline. So then reader and writer problem. This is one thing. Suppose this problem is, suppose, let me give an example. You are typing something in the Word and you have saved. So when we have saved, other person can use the same file and start editing it. And same way, even you are doing, the other person is also doing. Which one should be saved then by the operating system? That will be problem. Whereas reading, if we are reading, that is okay. Even you can read, your friend can also read. Then it will be okay, because you are not writing anything. That's what here we see. What are the problems when we, why we are facing in a readers and a writer problem? The reader and the writer problem is defined as follows. There is a data area shared among number of process. The data area could be file. The data can be your file or a block of main memory or a set of process register where you can read and write. You can read and write in a file. You can read and write in a main memory, or you can do it in a set of process register. These things you can do in a read or write. There are number of processes that only read the data area and a number that only write to the data area. The condition that must be satisfied are as follows. A number of readers may simultaneously read the file. So in case if it is a reader, I'm reading. Yes, 10 people can read the same file because we are not changing anything. We are just reading it. That is simultaneously it can be done. This reader options can be simultaneous. Only one writer at many write to the file. So this will be problem when many of them are started writing. Then only one, if a writer is writing to a file, no reader may read it. So in the same way, what the thing is, when if someone is writing, no others should read or write in that case. That's what the reader and writer problem. Thus, we can make out the writer wants every other process to be blocked for its execution. That's what when I'm writing. So when you are doing some project, no other person should do your or enter into your project and do something. That's what similar like that. When you're writing, no other process should enter. That should be blocked. Whereas reader need not block other process. When you're writing, only then should be blocked. When I'm reading, it is okay because no one, it's okay and not required to block. That's what the reader and writer problem says to us. The problem can be solved with the help of semaphore. So to do this, this read and write problem can be solved using a semaphore. And to do this, there are two ways. A reader have the priority and writer having priority. So how we can do is, so we are fixing a priorities. So readers have a priority. Here, once a single reader has begun to access the data area, it is possible for reader to retain control of data area as long as there is at least one reader in the acting of reading. So what is that reader have a priority? So when 10 people are reading, yes, no problem, because only reading, we are not changing anything. The procedure is explained here. The first reader block, if there is a writer, so suppose if someone is writing, any other reader who tried to enter the block to be blocked. While exiting, the last reader gives signal to a wait writer. So suppose if 10 people are reading, 11th person want to write. Then what? All 10 people completed reading. Then the last 10 person can give a signal for a 11th process saying that okay, you can start writing. That's what here it is. When writer exits, if there is both reader and writer waiting, which goes next dependent on the scheduler. Suppose sometime reader is also waiting, writer is also waiting. So this scheduler has to be fixed for the next thing. If the writer exits and the reader goes next, then all other waiting readers will get a chance to access. But in this methodology, writer are subject to starvation. That's what. If uh, keeps on waiting. So if writer exits and read goes on waiting, how long to wait? Then this may go for a starvation. In the same way, writer have properties. When we are writing, even there also we have a priorities. Unlike the previous case, here writer are decision maker. No new reader are allowed to access data area once at least one writer has declared as desired to write. This is accomplished by forcing every reader to lock and release the semaphore individually. So what we do here is writer have a priority. The writer, on the other hand, don't need to lock it individually. Only the first writer will lock the semaphore, and then all subsequent writer can simply use the resource as it gets freed by the previous writer. The very last writer must release the semaphore, thus opening the gate for a reader to try reading. So what we do here, read and write, is write can be done simultaneously, no problem. Well, there will be problem only when writing is being done. In this methodology, the reader may starve. In both situations, using semaphore will lead to a starvation. So what do we mean by starvation? Even the meaning of starvation is one people waiting. How long he should wait? 1 day, 2 day? Then that situation is called as a starvation. So another solution using message passing can be adopted. So to overcome this, message passing can be adopted. In this case, there is a control process that has access to the shared data area. Other process wishing to access the data area send a request message to the controller or granted access with an OK reply message and indicate completion of access with the finished message. The controller is equipped with three mailboxes, one for each type of message: a request, an OK, a finished. It may receive the controller process receives write request message before read request message to give write priority. In addition, mutual exclusion may be enforced. So this is about your read write problem, reading and writing problem. So by this, I complete your second unit. So next we move on to a third unit. That is what is called, the third unit is deadlock and memory management. So first we see what is deadlock. So before we moving on to a deadlock, I just want to give you a small example. Suppose we have only one bridge. Suppose you say that from one village to another village, I have to go from one village to another village. There is only one bridge, and down there is a water. And there is, because there is only one bridge. So then what is the problem here? And the bridge is very small. Only one vehicle can pass. So in that case, what we do? From one village, one vehicle has to come and reach the other village. Then only the other village people vehicle can go. So suppose if the two sides also people are waiting, let that village people come, and this village people will think that uh, uh, two villages think that okay they are coming, or these people think these people. So like this, one waiting for other waiting for this. No one is using the bridge. Then that situation is called as a deadlock. Okay. So now what is the principle of deadlock? Deadlock can be defined as a permanent blocking of a set of process that either compete for system resource or communicate with each other. So principles of deadlock is what? Blocking. So that's what here in deadlock, I told what do we mean by deadlock is, that's what one, if there is only one bridge and the two villages people are keep waiting, then that situation is called as a deadlock. It can be for, I gave you example for bridge, but in the operating system, this can be for a resources. Resources means one wants a CPU, one process wants a CPU, and other process also wants a CPU. Because this process wants a CPU, this is waiting. That process is also waiting. So like the CPU is not being utilized, both the process are waiting. That procedure is called as a deadlock. Not only with resources, it can be communicate with each other. A set of processes is deadlocked when each process in the set is blocked, waiting an event. Typically, the freeing up of some request resource that can only be triggered by another block process in the set. Deadlock is permanent because none of the event is ever triggered. So what is deadlock? Deadlock is a permanent because none of the events are triggered. And under the normal mode of operation, a process may be utilize a resource in only the following sequence. So how the operations can be done? You request, use, release. Okay. So let us take a phone call. So how do we call for other? Suppose you want to call to your friend. What are the steps you are doing? You take your mobile, go for a what you do? Go for your calling phone, then no, type your friend's number, then say call. Then what it will do? It will connect to your friend's phone number. That's what request. You're requesting for a communication. After you speak to your friend, then what you do? Uh, end your call. That is what release. So that's what we are doing here. Request, use, and release. This is similar like our calling. Not only calling, you can say anything. Your WhatsApp also, how we do, you request. You request for request. This will go back. Request, use, and release. Uh, that will suit for your phone calls, but it also suits for WhatsApp. But what here it is doing is not every time, even after he ons his net, then it will go. That's why we have a tick mark. So request, if the request cannot be granted immediately, for example, that resource is being used by another process, then the request process must wait until uh, can acquire the resource. So what is this request? That's what. Take one more example. You are calling for your friend, but your friend is speaking to his parents. Then what you'll get? What you'll get? You'll get a call saying that he is speaking to someone else. Then what you have to do? There is options. They'll give you options even in the phone. Either you can wait or you can call after some time. So then what we do? We have to wait. That's what you're wait. Suppose if he comes and if he ends his parents' call and he uses your phone, then use. The process can operate on the resource. Release, both of you spoke, then end. The process release the resource. That's what this request, use, and release. But if every process in the set is waiting for other process to release the resource, then the deadlock happens. That's what here deadlock happens when keep calling, and you keep waiting, and he is also waiting. That is the deadlock happens. Two general category of resources: reuse and consumable. Reuse is what can be safely used by only one person at a time. So what we do, that's what. Now, when you call, or you can call only for one of your friend. But now the technology has improved. You can call for many people. You keep a call on hold, then connect to other people. So like this you can do. But this is general basic one. What we do at one particular time, we are calling, we are connecting, and is not depleted, and that is not reduced. But by that use. For example, process, it may be process or input output channel, or it may be main memory or secondary memory, or any device or data structures such as files, database, and semaphores. Here, deadlock occurs if each process holds one resource and requests the other. So what is an example? uh, you have two assignments to write. One is OS and one is Java. And your friend is writing Java and you are writing OS. Then what you will be discussed, as soon as he completes Java, he has to give you the Java, and you, as soon as you complete the OS, you will give. But what you will be doing, let him give, let him complete, let him first give, and he will think, let him give. So like this situation is called as a deadlock. Consumable, one that can be created, produced, and destroyed, consumed. For example, interrupt, signal, message, and information in input output buffer. Here, deadlock may occur if the receiving message is blocked. So conditions or characteristics for deadlock. When do we say deadlock? Following are the condition for deadlock to present. So what are the characteristics we see for a deadlock? One is mutual exclusion. Another one is hold and wait. No preemption, circular wait. So these are the four characteristics for a deadlock. First one is a mutual exclusion. Only one process can use a resource at a time. So what it says, what this will say, uh, hmm, there should be only one process and one resource. That is what is called as a mutual exclusion. Hold and wait, a process hold at least one resource, is waiting to acquire additional resource held by other process. This is called hold. I am holding one process, but I want one more process. This is what is called as a hold and wait. No preemption. We have seen even in the scheduling also, no preemption means until unless my work is completed, I'll not leave. That's what is called as a no preemption. A resource can be released only voluntarily by the process holding it after the process has completed its task. That's what no pre. Circular wait, there exists a set, there are so many processes, P0, 1, 2, 3, like this n of waiting process, such that P0 is waiting for the resource that is held by P1, and P1 is waiting for the resource held by P2, and so on till Pn minus 1 is waiting for the resource held by Pn, and Pn is waiting. So like this circular waiting. I'm waiting for my friend. My friend is waiting for his friend. His friend is waiting for his friend. Like this is called as a circular wait. First one, resource allocation graph. So the resource allocation graph is a directed graph that depicts a state of the system of the resource and process, with each process and each resource represented by a node. If a graph consists a set of vertices V and a set of edges E with the following notations. V is what? Partitioned in two types, P and R. What is P? P, set of processes. How many set? How many processes we have? P1, P2, P3, like that, Pn. And what is R? R are a set consisting of our resources. So what are the resources? Suppose I am a staff. How many staff we are in our department? 12. And how many resources or how many computers we have? We have so many computers. But suppose if lab is going on, then how the staff can use? Staff cannot use the resources. That's what here resources. A request edge, a directed edge, that is PI, requesting for RG. What is that? Process PI requesting for resource RG. Indicate that the process PI has requested for an instance of the resource RJ and is currently waiting for that resource. Then assignment edge, a directed edge RJ tends to PI, indicate that an instance of resource RJ has been allocated to the process PI. That's what here you can see how to draw a graph. So the circle, we call it as a process. The following symbols are used while creating a resource allocation graph. First one, what it says, only a circle without anything blank, that is a process, one process. And was a rectangular or a square is called as a resource. And within that resource, how many processor or instances are there? There are four instances. In this diagram, there are four. Okay, now come back to the third one. PI, a mark, a line with the arrow mark, where it says that PI request for RJ. Process PI is requesting for RJ. Okay, and the fourth last diagram, process PI is holding an instance of RI. So what it is, you can see the arrow mark is in the reverse. PI is holding a resource RJ. So these are the symbols we use for drawing a graph. Okay, examples. Let us see how to draw this graphs using these symbols. We have just shown these are the symbols where we use to draw a graph. So example for resource allocation graphs are shown in the figure 3.1. We see in 3.1. Note that the figure 3.1, see the process P2 and P4 are not depending on any other process, and they will give up the resource R1 and R2 once they complete the execution. Hence, there will not be any deadlock. So you can see here in this resource allocation graph, I told you we have just shown what are the diagrams depicts here. What is the circle depicts us? What is circle stands for? Why do we use a circle? Yes, answer. Why do we use a circle? Why do you use a rectangle? Yes, anybody? Yes, why do we use? Why do we use a circle? What is the use of this? Okay, circle is used for process and rectangle is used for resources. And which resource what? That's what here in this diagram we showed. Circle is a process and rectangle or a square we called resources with four instances. Process I request for RJ, and the last one says that process PA is holding the instance of RJ. And this example resource allocation graph, you can see here how many resources we have. We have three processors P1, P2, P3. All these circle one is called as a process. How many process we have? 1, 2, 3. P1, P2, P3. How many resource we have? We have four resources: R1, R2, R3, R4. Okay, so here what it is, P1 is requesting for R1. So P2 is using resource R1. P2 is requesting resource R3. P3 is using R3. So the same way here, R2. R2 is being used R2 resource. Again, within that request resource in R2, part of it is used by P1, part of it is used by P2. And R4 is no one is using a R4 resource. So that's what resource allocation graph says to us. Come back to here. When do we say deadlock? P1 wants R1, P2 is using R2, so P1 has to keep waiting. Same way you can see R3, P3 is using R3 and P2 wants R3. Then P2 has to wait until R3 is released by P3. So in the same way, R2. R2 is used by P1 and P2 and they will not release. If because they are not releasing, P3 wants R2 and this is called as a deadlock. Deadlock means one is using resource, another is not leaving. This process is called as a deadlock. Why cycle but not deadlock? So we can remove this deadlock by making it as a cycle. So you can see in the last graph, P1 is P1 is requesting for resource R1. So R1 is used by P2 and P3, and P3 request for R2. P4 also using resource R2, and P1 is also using R2. So this is what is called as a resource allocation graph. The same explanation here. Given the definition of resource allocation graph, we can understand that if there is no cycle in the graph, then there will be a deadlock. If there is a cycle, there is a chance of deadlock. There are three general approaches exist for dealing with the deadlock: prevent deadlock, avoid deadlock, detect deadlock. So how the general principle or general approaches exist for dealing with the deadlock is: first, you see to that prevent the deadlock. See to that deadlock should not occur. If it is occurred, then try to avoid the deadlock. Or one more option, detect where the deadlock has occurred. These are the three approaches where we see with the deadlock. Prevent deadlock. How to prevent deadlock? Same way here. So before any disease, that's what there is one proverb: prevention is better than cure. Yes, means what? Instead of after you get some disease and get uh, curing, that is very difficult. So that's what prevent. Same way here, now you can see what all whole world is doing. It is uh, keeping social distancing, and we have to stay back to keep our country safe. We have to stay at home. What we are doing? Preventing. What we are preventing? Coronavirus should not reach to us. So that's what we are trying to prevent. So cure by mistake, if corona is attacked, then it is very difficult to come out of that. So then what? Either there are only two options right now. Either you have to die or come back if your immune system is very good. That's what here. The same approach here. Prevent deadlock. Ensure that the system will never enter a deadlock state. Or avoid deadlock. Make appropriate dynamic choice based on a current state of resource allocation. So what we do here, avoid deadlock, make appropriate dynamic choice based on the current state of resource allocation. So you see and see which resource is free now you can do. Let us take an example. You want to go for a movie and there are four queues. In that four queues, two queues are full, another two queues are free. Then what you do? Definitely we go for a third and fourth queue because they are free. Same way here also, to avoid deadlock. So dynamically you take a choice. Then detect deadlock, allow the system to enter the deadlock state, then recover. Last one is a detect and detect the deadlock. So first one, what we have told, deadlock prevention. So to do this, what are the steps we have to follow? The strategy of deadlock prevention is to design a system in such a way that the possibility of deadlock is excluded. This is possible if we ensure that one of the four conditions, mutual exclusion, hold and wait, no pre-emission, and circular wait, cannot hold. So when do we say we can avoid or prevent deadlock to occur? When we say these four conditions we don't hold, it is not happening, then we say it is we are preventing a deadlock. What are those four conditions which we have already seen? Mutual exclusion, hold and wait, no pre-emission, and circular wait. I will stress deadlock definitely is one question which is will come in your final exam. We will examine these conditions now. So mutual exclusion. The mutual exclusion condition is what must hold for non-shareable resources. So what is mutual exclusion? When should you go for mutual exclusion to avoid deadlock? So non-shareable. So I don't want to share anything. Non-shareable, then you can go for a mutual exclusion. For example, printer cannot be simultaneously shared by several processes. That's what. Printing cannot be done by four people at a time. Only one work or one page of printing will be done at one time. That's what the mutual exclusion is. On the other hand, shareable resources do not require mutual exclusion access and thus cannot be involved in a deadlock. For example, simultaneous access can be granted for read-only file. Process never needs to wait for a shareable resource. So when do we say? I think you would have been seen sometimes when we open any downloaded thing, then there will be some option called as this is only read only. What do we mean by read only? Means I cannot edit anything in that. I can only see. I can only read. Then in that case, this simultaneously I can have so many read-only files. That's what here it says. In general, we cannot prevent deadlock by denying the mutual exclusion condition. Some resources are intrinsically non-shareable. That was a mutual exclusion. What the mutual exclusion says to us is, you see to that you use the resources which are not shareable. That is what is called as a mutual exclusion. One more condition what we have is hold and wait. To ensure that hold and wait condition never occur in the system, we must guarantee that whenever a process requests a resource, it does not hold any other resource. That is, the process should all its request all its required resource at one time and block that process until all its resource requests are can be granted simultaneously. What it says hold and wait is, if you have one process and you cannot request another one until unless you release this. That's what is called as a hold and wait. The process may be held up for long time waiting and for all its required resource. Actually, it would proceeded with only few of the process. Resource allocated to one process may remain unused for some time, during which they are denied to another process. Process may not know in advance all the resource that it requires. That's what here hold and wait. What is hold and wait says to us, to avoid deadlock, see to that if one process is using one resource, until unless it releases that resource, other one should not be allocated. That's what here it says hold and wait. Next one is no pre-emission. This condition can be prevented in this way. If a process is holding some resource and requesting another resource that cannot be immediately allocated to it, then all resources currently being held are pre-emitted. In other words, the resources are implicitly released. The pre-emitted resources are added to the list of resources for which the process is waiting. The process will be restarted only when it can regain its old resource as well as the new resource that it requests. This is what is called as a no pre-emission. And the last condition where we can see to that deadlock is not happening is one, circular wait. The circular wait condition can be prevented by defining a linear order of resources. Linear order means give a order 1, 2, 3, 4. Like this, you have an order for your USN. Why do we have your USN order? So that alphabetically order USNs are there to identify uniquely. So the same way, in circular queue also, that is, every process must request the resource in an increasing order. Let there be a two process P1 and P2. Let there are resources Ri and Rj such that I is greater than j. Now Pi has acquired Ri and requested Rj, and P2 has acquired Rj and requesting Rj. The condition is impossible because it implies that I should be less than and j should be greater than. But here also the problem seen in the hold and wait preventions are seen. Okay, so that was about deadlock prevention. So, what do we mean by deadlock? We have just seen that it is a permanent block. We don't want any either it may be with respect to resource or communication where it will block. We don't want to happen that. So in that case, these are the four conditions where we say a deadlock is present. When do we say deadlock is present? When these four conditions satisfy: mutual exclusion, hold and wait, no pre-emission, circular wait. If those four conditions are there, then we say it is deadlock is present. To overcome deadlock, what we have to do? We have to say that we have three approaches to see to that deadlock should not occur. What is that? Prevent deadlock, avoid deadlock, detect deadlock. So then first one is a deadlock prevention. How to prevent this? When four characteristics, that is mutual exclusion, hold and wait, no pre-emission, and a circular queue. These four, you see to that it will not happen. then automatically the deadlock will not be happening. That's what we have seen. Next, we move on to a deadlock avoidance. So what do we mean by avoid? That's what here, right now, what we are doing, we are trying to avoid ourselves from coronavirus attacking us to at staying home. That's what, same way here also, deadlock avoidance. So deadlock prevention method seen in the previous section requires at least one condition should not hold. What do we mean by deadlock avoidance or prevention? Deadlock prevention method seen in the previous section requires at least one condition should not hold. But these methods results in low evidence, low device utilization and reduced system throughput. An alternative method for avoiding deadlock is to require additional information about resource to be requested. This for this purpose, a simplest and most useful model is designed. Each process must declare a maximum number of resource of each type that is it may need. So what is deadlock avoidance? So suppose one process, I'll say that I want this input at this time. I want this at this time. Then we say pre only, before only, so that deadlock is not deadlock can be avoided. Given a prior information about a maximum number of resources of each type that may be requested for each process, it is possible to construct an algorithm that requires that the system will never enter a deadlock state. This algorithm defines a deadlock avoidance approach. Okay. So what type of algorithm we are saying? Deadlock avoidance approach. Deadlock avoidance algorithm, what it says, dynamically examine the resource allocation state to ensure that circular wait condition can never exist. The resource allocation state is defined by number of available and allocated resource and the maximum demand of the process. Okay, allocating resource. Safe state. A state is safe. When do we say? So when we are just calling you and saying that whether you are safe or not. What do we mean? We ask you whether you have any fever, cold, cough. Because of these three only we say corona is attacking. That's why we call and ask. Same way here also, safe state. A state is a safe if the system can allocate resource to each process in some order and still avoid deadlock. More formally, a system is in a safe state only if there exists a safe sequence. When do we say safe state? We, when there is a process in some order, there should be some order like 1, 2, 3, 4, 5. There is an order here, increasing order or decreasing order, 10, 9, 8, something like that. That's what means some order should be there. Along with that, there should be a sequence. Sequence means one after the other, one after the other, safe sequence. The sequence can be P1, P2, P3, Pn. Is a safe if for each Pi, the resources that Pi can still request can be satisfied by a currently available resource plus resources held by all Pj with that condition. What is that? J should be less than I. This is what is called as a safe state. So what are the three steps we see in the safe state? If the need of Pi are not immediately available, then Pi can wait until all Pj has finished. What is the first step in the safe state? Suppose I'm requesting something. When I'm requesting, that is used by Pj. Then what I have to do? I have to wait until this Pj releases everything. That is the first. Then what is the second step? When Pj is finished, Pi can obtain needed resources, execute, return allocated resources, and terminate. What is the second one? When Pj is finished, now Pi can take, execute its work. Then whatever work is done after completing, it can give back. That's what the second step. What is the third step says? Pi terminate. Pi plus one can obtain its needed resource and so on. Like this, I will complete my work. After I complete, I'll give you. That's the same thing you do with your assignments also. First you see either your record or anything. First you sit and write. After you complete, you give that record to your friend. Let him complete his record writing, then he will give to his friend. Like this process is called as a safe state. So that's what here, safe and unsafe. When do we say it is a safe? That's what I write. I will not give you until I complete my work. That's what is called safe. If no such sequence exists, then the system state is said to be unsafe. So deadlock, unsafe, safe. So that's what here in this diagram it depicts how the deadlock uh, can be avoided. And when you say it is not in safe, then it is called as an unsafe. If it is unsafe, then definitely deadlock will occur. That's what the picture depicts here. A safe state is not a deadlock state. So that's what here in this diagram you can see. Safe means what? The deadlock will not occur. When do we say deadlock will occur? When the state is in a unsafe state, then only the deadlock will occur. A safe state is not a deadlock state. A deadlock state is an unsafe state, but not all unsafe states are deadlock as shown in the figure 3.2. But here in this case, you can see all unsafe states, we cannot say it is a deadlock. An unsafe state may lead to a deadlock. As long as the state is safe, the OS can avoid unsafe states. That's it. You can try to avoid until unless we are in a safe, the deadlock will not occur. In an unsafe state, the OS cannot prevent process from requesting resource such that the deadlock occur. The behavior of the process controls unsafe state. Okay. So next, resource allocation graph algorithm. So we have just seen in the earlier slides how the graphs, how to draw graphs, what is a process, how to draw, which are the diagrams. So now see algorithm, how the resource allocation can be done for the algorithm. One of the technique for avoiding a deadlock is using resource allocation graph with an additional edge called as a claim edge. Claim edge is what? So in your graph, if I have two nodes, a line drawn between these two nodes is called as a edge. So in that edge, we call it as a claim edge. Claim edge means which is a source and which is destination. So that's what you can see here. Claim edge. PI wants a RJ resource. So that's what it is requesting for the resource RJ, indicating that process PI may request resource RJ at some time in future. This edge is represented by a dashed line. The important steps are as below. When a process PA requests resource RJ, the claim edge PI arrow mark RJ is converted to a request edge. Similarly, when a resource RJ is released by the process RI, the assignment edge, reverse of it. RJ releases the uh, PI is reconverted as a claim edge. Then it is we call it as a claim edge. The request from RJ from PI can be granted only if the converting request edge to the assignment edge do not form a cycle in a resource allocation graph. So when do I can allocate resource allocation? When it is not forming a cycle, then only we can request claim edge. To apply this algorithm, each process PA must know all its claim before it starts executing. If no cycle exists, then the allocation of the resource will leave the system in a safe state. If this cycle found, the system is put into unsafe state and may cause a deadlock. So an illustration, consider a resource allocation graph shown in the figure 3.3. Suppose P2 requests R2, though R2 is currently free, we cannot allocate it to P2 as this action will create a cycle in the graph shown in the figure. We'll see in the next. If this cycle will indicate the system is unsafe state, because if PI request R2 and P2 request R1, later it will a deadlock will occur. That's what you can see here. What is dashed line says to us? I may require. That is P1 says that I may require R2 and P2 also says I may require R2. Now R1 is used by the P2, P1. P1 is using the R1 and R2. So this state can move into unsafe or a deadlock allocation. For deadlock avoidance, we should not form a cycle. That's what here an unsafe state. It is not a safe state where it is a unsafe. So this is what is a resource allocation graph says to us. So I'll stop here and we continue in the next class.
Thank you, ma'am.